Yeah, g'day, it's Charlie ZL2CTM. So I just want to spend some time on this video looking at the crystal filter, and I'll probably start doing the single sideband filter first and then move on to the CW filter. And you'll recall from a previous video that I want to try and use the approach here by Wes Hayward that he presented back in QST in 1987. Seems to be a very simple way of making a cone filter using any number of crystals with the same value capacitor in series at the input and output, and then across between each crystal and ground. So this is the approach I want to take. This particular paper here talks about 3 steps. First is identifying the crystals, and it talks about here about having the crystals within, when you choose, and I'm going to use 4 crystals for at this stage for the single sideband filter, and I'm thinking about 6 for the CW filter, just to get some really nice tight skirts. Now it talks about here when selecting those crystals, you want to have the crystals within 10%, so the frequency error across those crystals less than 10% of the desired bandwidth of the filter. So if I'm going to pick on, say, 200 or 2700 Hertz or 2.7 kilohertz for the single sideband filter, then 10% of that is 270 Hertz. I'm going to go. So here's the example here. So 1 kilohertz or 1000 Hertz, 10% is 100 Hertz. I want to go much better, if I can, than the sort of the standard rule of thumb, which is 50 Hertz variation between the crystals. So I'm going to do that in 2 ways. I'm going to start by using a simple Colpitts oscillator here, using a 3904 running off 9 volts with some simple biasing here. There goes our split capacitors for the Colpitts, 2 220 picofarad capacitors, and then between the base and earth will be our crystal under test. So I'm going to grab those 100 crystals I got from China, and we'll run them through this little test set here, or oscillator I should say, and then just using a little fly lead here, loosely couple this through to 2 things for a start. The first, I'm going to use this SDR dongle here. It's the old RTL SDR. To I guess in a coarse way identify some crystals that are close to each other, and then I'll talk about the second method to fine tune those even further. Now this particular SDR dongle here is a version 3 dongle. You can just see there version 3. The beauty of the version 3 dongles is it allows you to, through the software, and I'm using SDR Sharp, which we'll look at in a sec, it allows you to tap into either the normal quadrature output from these devices, which is your in-phase and quadrature signals, or you can also tap into either the quadrature or the in-phase signals. Now in this particular case, if I tap into the quadrature output of this, I can actually tune SDR Sharp down into the HF region, because typically these devices here, certainly the version 2 and earlier, we're restricted to VHF and above. So unless you built a down converter to mix that higher frequencies down, say again the HF, and mix it up into the VHF band, you couldn't use them. But the version 3 devices are different. So up on the screen here we have SDR Sharp running, and of interest here is, if I just pause, sorry about the reflections there, if I just stop that and go into settings, so under that generic device, which is our dongle, under sampling mode, you'll see here that rather than the normal quadrature sampling, I've selected direct sampling Q branch, or the quadrature branch. So by clicking on that and then starting it, it allows me to tune down into the HF band. And what I've done here is, like I say, I'm going to use this in a coarse way. So there goes our 9 megahertz signal there. Now these crystals appear to be resonating on the series resonant frequency, which is slightly lower than what's marked on the side, but that's fine, all things being equal. So I'm just going to use the zoom function here to zoom up to, I don't know, somewhere around there, noting that I'm loosely coupled. So down here, I've got the antenna hanging off the SDR sharp, and I'm sort of in the region of that orange wire there, which is the emitter on the output of that Colpitts oscillator. So I'm just going to, for a start, get the center frequency to be roughly, using the old Mark 1 eyeball, roughly halfway or in the middle of that particular signal there. And then up here I can use the frequency counter, so 8.997095, to then write down on the side of the crystal the frequencies. I'm going to use the last 4 digits there, so 7095, because these values here, 8.99, is not going to change across all of those 100 odd, well I hope they don't, 100 odd crystals. So I'm going to do that for a start, and then I'm going to use, I'll just show you now, a different method to then fine tune those to work out exactly what the frequency is. The best, or as much as I can do with the equipment I have here in the shack. So I have down here a crystal that's sitting in that crystal oscillator. I'm taking its output and I'm loosely coupling it to my oscilloscope input using a 10 picofarad capacitor. So again, this is stage 2 now, so we've been through the SDR program and we've got a number of crystals which appear to be close to each other. So I'm loosely coupling that through the oscilloscope. I've got the probes on times 10, so just trying to minimize the loading on that particular oscillator there, and feeding that into the oscilloscope. Now the second input I'm taking from the SIGGEN, and I'm going to tune the signal generator to be close to, and we'll look at what the effect's going to be to the frequency that's coming out of the signal generator. So sine wave, and I've adjusted the amplitude to give me the same, let me just move it off to one side, the same amplitude as what's coming out through channel 1. So if we go to channel 1, so let's take it off that mode there. Channel 1 is the output of the crystal oscillator, and channel 2 is the output, and I'll just trigger off 2, is the output of the signal generator. And I've adjusted the amplitude or the magnitude of the signal generator to give me the same amplitude between 2 inputs. Now if I go to X and Y mode, X and Y, trigger off that one, I can then start to create the phase symbol here, and I won't pronounce the French name because I'll get it wrong. Now if I get the frequency to be essentially the same, I'm going to create some symbols here. Now depending on which way it's facing, a diagonal line in this direction here would be 0 degrees. A full circle there is either going to be 90 degrees or 270 degrees phase difference between those two frequencies, moving through to 360 and 180 and the like. But the key here is when it's passing through that sort of 90 and 270, I've only got one circle as opposed to a figure of 8. So that one circle is telling me that the two frequencies coming in are the same frequency. And the fact that it's now rolling around and around and around is I don't have phase lock. So the phase difference between those two frequencies is sort of moving in time. Now the other thing too of interest, I've just got down here just a sort of another way of you could use if you wanted to work out a similar frequency, is to use a say a general coverage receiver here. So this receiver is currently tuned to 8998. So I'm getting roughly a 1 kilohertz tone difference between what's coming out of our oscillator and our SIGGEN. So if I was to turn that volume up, you'll hear a solid tone. Now if I was to tune, and let me just do it up here, if I was to tune our SIGGEN off, you start to hear that warbling sound. Well, that warbling sound is a beat frequency. And if I was to come across the O-scope, so basically, as it expected, the beat frequency between the two signals becomes 0 when the two frequencies that the general coverage receiver is receiving are the same. So that's another way you could, if you wanted to try and work out if you're on the same frequency or not. So without the O-scope, what we could have done is used our SIGGEN here, and then assuming that this is our unknown, the crystal in our oscillator, by using this we could then tune for 0 beat. And it's better if that's sort of near the SIGGEN. And then we can use the fine tune here. So this is down to ones of hertz. So to me there, that's spot on frequency. So with some confidence I can say, you know, all things being equal in terms of the errors of all the circuitry here, that crystal is oscillating at 8.997090 hertz. So I'm actually going to jot down on my bit of paper 7090, and I'm going to do that for all the other crystals that I think are roughly within cooey of each other, and I'm trying to get, in terms of those last two digits there, the 9 zeros, if we get those two there, that's ones of hertz and tens of hertz. So in an ideal world I want to get 4 crystals that are less than 50 hertz of each other. And if I can get considerably better than that across these 100, that's what I'll certainly do. And just for interest's sake, with that beat frequency disappearing, again, if you look up here now, we're pretty well on spot on. So anyway, that's step 1. So if we go back to our instructions here, let me just turn that down because it's a bit annoying. So step 1 was to obtain a collection of substantially identical crystals within 10% of the bandwidth. So like I say, we're going to be considerably better than that. And then we'll come back and we'll pick this capacitance, and then we'll do some plotting with the SIGGEN and the O-scope, and we'll plot the frequency response, and we'll go from there. So according to the paper here, by varying the capacitance we will vary the bandwidth, and then by varying the terminal resistance to work out a good match, and we're trying to work out what the impedance is going to be, we'll vary the ripple across the passband. So that's the plan, and I will pause here and continue on with that. Cheers all. So through the process just before, I managed to get enough crystals at this stage to do 7 filters. For example, the leftover ones here, there was a group of 4 here that were within 21 hertz, another group here within 35, 30, 25, and here's a group here which was 16. I chose 2 lots that are not here. One was within 15 hertz. I got 4 of those which I'm using for the SSB, and another one which was around 20 hertz across the lot, which will be the 6 crystals I'll use for the CW filter. So the configuration is exactly as I've seen here. It's 4 pole, 1, 2, 3, 4 crystals, with our coupling capacitors on the input, and then the coupling capacitors to earth all being the same value. What I did for a start is I elected to just run with 150 picofarads as the capacitors on the input and to earth, and then just notionally chose, trying to sort of extrapolate some of the tables, or the table in that particular article chose 133 ohms. The capacitor there will set the bandwidth, and then the resistor there will be the passband ripple. So that particular configuration there yielded 1780 hertz, so not quite wide enough. As per the directions in the article, reducing the capacitance increases the bandwidth. So try to 100 picofarads is the next iteration. Came out at 2.2 kilohertz, and then the third iteration was 82 picofarads, which came out at 2490. So that's the one I decided to continue working on, and then elected to just vary the value of the resistance coming in and also across the output to earth. So in the end I used a couple of variable resistors, and in fact if I just look over here, that is the test filter at the moment. So in doing that final set of calculations using or trying to work out what the ripple factor was, I used two variable resistors here. They're both 500 ohms. So on the input, it was just a common leg and one of those legs, and it was left floating. So the assumption is that the SIG-gen is 50 ohms. So whatever resistance I was using, for example, let's say 100 ohms, then 100 minus the 50 from the SIG-gen would mean 50 here. So this was set to 50, and then the output would have been the full 100 from the output to earth with the scope over top. So that's what I used to sort of very quickly vary the input and the terminating resistor to try and work out what the passband ripple was going to look like. In the end, I settled on 200 ohms, and I desoldered these, and in the place just used two FT37-43 transformers, and the turns ratio on those, those are out of junk boxes, why the different colours, is 12 to 6. So 12 turns on the secondary, or the side closest to the filter, and then 6 turns on the outside on the 50 ohm side. So 12, as you know, 12 divided by 6 equals 2, which is the turns ratio squared, so 2 2s are 4, and then 4 times 50 would give us our 200 ohms being presented on either end of this particular filter. So next steps was to sort of quantify this a little bit better. So in the end, just used the SIG-gen, ran through sweeping it, using the oscilloscope to measure what the impact on the output was, and then used Google Docs to plot that. Let me go back to then using Google Docs to that's actually the input. Google Docs to plot what the output is. So hopefully up here this will come out. It's not got a bit of bars coming down from the monitor there. Anyway, there's two plots there. The top plot is just straight out the voltage coming out of the SIG-gen and the voltage across that 51 ohm resistor. So the output of that particular filter at the moment with that 12 to 6 turns ratio transformer has sitting on the output side a 51 ohm resistor. It's just measuring across that 51 ohm resistor and comparing the voltage across that versus what the SIG-gen is putting out here, which is a constant 1.94 volts, and plotting that. And then the second plot here is exactly the same values as inputs but converted to dB, and then just normalized. So just normalized the maximum to be 0, and then everything else comes from there. So looking at the calculations there, if my numbers are correct, the minus 3 dB point comes out to be 2750, so 2.75 kilohertz, and the minus 6 dB point comes out to be 2.97 kilohertz. I'm certainly open to I guess feedback on the approach taken to measure both the passband as well as I guess the test setup there. I really don't know if it's right or wrong. It looks about right. I guess some comments there. The insertion loss also, if my numbers are right, is minus 6.8 dB insertion loss between what's coming out of the SIG-gen and what's being presented across that 51 ohm resistor. Incidentally, even though this drops down to 30 dB down, if you do go out a couple of kilohertz, that gets down to a good 40 dB. Certainly not 90 dB. That's quoted on some of the commercial filters. Again, I'm not too sure if that's the process I used to measure this. In fact, it's a bit more interesting to look at rather than just a plot. I don't know if it was the method used to plot the output across this, or is it because these filters here, you know, crumbs, what did I say I think I paid? It was 20 New Zealand dollars for 100 crystals, so they're not expensive crystals in any way, shape or form. So, you know, there's a potential there that some of the capacitance within that is upsetting things. Yeah, I don't know. I'm not an expert in this field, so I'd certainly welcome any feedback or any comments which might help with that. But you know, potentially the stop band rejection is not as high as it could be. It could be that, you know, because these filters aren't the highest spec, say again these crystals aren't the highest spec crystals in the world, maybe there's a need there to maybe increase this up to a 6-pole filter to improve that. Again, I'm not too sure. One part of me thinks just to leave the SSB filter as it is. The bandwidth is about right. The skirts seem to be relatively steep between the -3 and the -6 dB points. So I'm sort of half tempted at this stage just to carry this through with the build and just see how it actually performs once it's configured as a super hit, and sort of see how it works in the real world. But like I say, more than happy and welcome to have some feedback there on the process by which this was measured. Again, trying to take a simple approach with simple equipment in the shack here without any kind of elaborate, be it crystal characterization circuits or tools or test sets and the like. So just trying to keep things as simple as I can there. This particular article, well, this particular article here didn't really talk about what to expect by way of performance. There were, halfway through, the ARRL staff here made some filters. The plots of those are on this page here. And they talk about so -40 dB for some of these filters in the stop band. So again, not entirely sure if that's good, bad or indifferent, and that's just to be expected with, it really is quite a simple approach to building a filter here, by just not even trying to characterize the crystals, but just by putting the same value capacitors in there to create that Cohen filter. So I'll leave it at that. I think the next step will be to do exactly the same process for the CW filter. That'll be a 6-pole filter, and nothing sort of too different there, just six filters, and then it'll be 8 capacitors there. Probably start with 200 picofarad caps. I'll probably start with 150 ohms, and we'll just see how that plays out, and we'll do exactly the same process and see if we can't create a CW filter. Rightio. There's just an example there of some of the plots when I settled on the 82 picofarads, just using various value resistors and then just doing the individual plots to see how they looked. And the reason why I settled on the 200 ohms in the end is it seemed to be the best in terms of straight sort of passband ripple, seemed to be the smoothest. So that's why I picked on that one. Extremes around here just made it worse. So it was around here somewhere was the sweet spot. Okay, well, I'll say 73s, and I'll put this video up. Like I say, welcome feedback, and next steps will be to work on the CW filter, and we'll see how that goes. Okay, cheers all.